For 20,000 years, the fundamental way we joined fabrics never changed. It relied on a needle passed entirely through a surface by human hands. Because every stitch had to be pushed and pulled manually, clothing production was a grueling, low-volume craft. That bottleneck lasted until 1830, when a French tailor named Barthélemy Thimigné patented a machine that used a hooked needle to form a chain stitch. By 1841, he had 80 of these machines sewing uniforms for the French army in a Paris factory. But the invention was seen as a death sentence for manual labor. A mob of 200 tailors, fearing for their livelihoods, stormed Thimigné's workshop and burned his machines to the ground. This wasn't just a technical setback. The riot proved that mechanizing the stitch was a direct threat to the established economic order of the working class. The innovation shifted to America, where Elias Howe patented the lockstitch in 1846. His design was mechanically functional, but Howe lacked the business connections to sell it, eventually leaving the country to find work in England. While Howe was away, Isaac Singer refined existing designs into a more practical machine, featuring a foot pedal and a vertical needle. Unlike Howe, Singer was a marketing expert who built a massive manufacturing empire around the device. When Howe returned to find his invention being used by others, he sued Singer and dozens of other manufacturers. This triggered the sewing machine war, a period of aggressive litigation where every major inventor claimed the others were thieves. The legal gridlock brought the industry to a halt. No single company could build a high-performance machine without infringing on a rival's patent, leaving manufacturers mired in lawsuits rather than production. In 1856, the rivals reached a compromise. Singer, Howe, and two other major firms pooled their patents into the sewing machine combination. This allowed them to cross-license the technology while charging all other competitors a high entry fee. By sharing their intellectual property, these bitter rivals standardized the technology. They stopped fighting in court and started dominating the global market as the world's first millionaire inventors. Early inventors failed because they tried to replicate the motions of a human hand. They built mechanical pincers to push a needle all the way through the cloth and catch it on the other side. This push-pull motion was too complex for the gears of the era to perform reliably. The breakthrough came from a counterintuitive change, moving the eye of the needle from the blunt end to the sharp point. With the thread at the tip, the needle never has to leave the machine's control. It simply punches into the fabric and retreats along the same path. Abandoning the goal of imitating human fingers in favor of this machine-specific logic is what finally made automated sewing possible. However, because the needle only pokes through and retreats, engineers needed a new way to secure the thread, or the stitch would simply unspool. This is where the lock stitch comes in. The top needle punches down and then rises just a fraction of an inch. That slight upward movement causes the thread to buckle, creating a small loop beneath the fabric. A rotating hook positioned under the table then catches that tiny loop of slack. The hook drags that top thread entirely around a second spool of thread called a bobbin. When the needle pulls back up, it pulls both threads taut, interlocking the two in the center of the fabric. This interlocking geometry became the definitive standard for machine sewing because it created a seam that wouldn't unravel even if a single stitch broke. The final bottleneck was movement. To sew continuously, the machine needed to advance the fabric evenly so every stitch was perfectly spaced without the user pulling it by hand. Alan B. Wilson solved this with the four-motion feed. These metal teeth, or feed dogs, follow a rectangular path. They rise to grip the fabric, pull it back exactly one stitch length, drop down to release it, and move forward to reset. Syncing these automated teeth with the needle eliminated the final human constraint, letting the machine sew as fast as the operator powered the drive wheel. In the home, the impact was immediate. It took roughly 14 hours to sew a man's dress shirt by hand. With a machine, that same shirt could be finished in an hour and 15 minutes. This reduction in labor freed middle-class women from days of domestic mending, turning the sewing machine into a prized appliance that offered more hours for leisure or outside work. But in the commercial sector, this efficiency was used to increase demands on workers. Because sewing was now faster, clothing manufacturers moved away from small tailor shops to large machine-controlled factories. This shift birthed the sweated labor system. Factory owners demanded higher volumes at lower piece rates, forcing workers into grueling, tightly controlled environments to earn a living. By the 1860s, this system had already transitioned America toward ready-made garments produced at a massive scale. As prices dropped and supply increased, the industry began a cycle of rapid production and consumption that eventually expanded into the modern global fashion market. The mechanics of the sewing machine solved a physical constraint that had lasted for millennia. However, by prioritizing mass efficiency and piece rate speed, the early industry established the high-volume, high-waist model that continues to define apparel production today.